Hello and welcome back to this course on computer organization. So in the last couple of weeks, we looked at various instructions of the x86 architecture, namely the move, the ALU operations, the branching and looping, that is the jump instructions. Then we looked at the stack instructions, push and pop, then the call and ret. Okay. So in this video, we are going to look at some very special instructions that are available only with this x86 processor. So the other instructions I spoke about are generally available almost in any processor in some form or the other, as you will see later in this course as well. But the instructions I'm going to talk about today, right, are basically instructions which are very specific to the x86 architecture, and that is called the string instructions. Okay, so the idea here is many times we deal with data, okay, in sort of in a register, or we deal with 32 bits of information at a time, and we try to do some manipulation or the other, ALU manipulation with it, but typically restrict ourselves to either 8, 16 or 32 bits at a time. But there are also many scenarios where we would like to move like maybe chunks of data, right? We may want to either move a big chunk of data from one portion in one segment in the memory to another segment, or one region in the memory to another region, because segment has a very special meaning in the x86 architecture, right? Or for that matter, you might want to specifically compare two strings, or you're trying to look for a certain character and so on, right? So these are the kind of scenarios that we might want to deal with, and therefore x86 does provide some instructions which are very specific to these string type of operations or the array type of operations. Okay, so the first thing we are going to look at is data movement. Right. So the instruction for data movement, if you remember, was just a MOV, right? And then we gave a destination register comma source register, or a destination location comma source location, right? But now what we are going to do is, we are not just like the push and pop, right, where the registers that were being used were sort of implicitly were implicit, right, like the ESP, stack pointer, right? In this case, we are going to implicitly use two registers for these specific string instructions. Okay, so the instruction, by the way, is called MOVSB. Okay, I'll tell you what this thing is. So the move is, of course, we are moving. S is for string and B is for byte. Okay, now what does this actually mean, right? So if you go back to the memory picture, right, so this is going to be broken into many segments. So let's assume the small one, this is code segment. Okay, this is stack segment, right? Because I'm just going to deliberately deal with some data in the data segment and extra segment, so therefore I am going to simply keep it like this. Okay, this is my data segment, right? Right, and this is my extra segment. Okay, now let's assume that I have some data which is sitting here like this. Okay, so this is, wait, right, so let me deal with it like this. Okay, so some data, that is some byte of information that's eventually starting with blue and then it ends in magenta. Let's assume that there is different random data that is going to sit in these memory locations. Okay. Now, let us say that, so in this data segment, what do I have? I have how many memory locations here? Each row, by the way, is 1 byte of memory. Okay. So, I am basically saying this blue data, whatever that is, it's an 8-bit number. Okay. For example, this blue could be something like 0xFE. You know, the magenta could be 0xAA, some other random number, right? I'm just giving a color to indicate that data. Okay, so that's an 8-bit number and it basically is a byte of information. Okay, let us assume that I want to move these 6 bytes of information from blue to magenta. I want to move it to another region in the memory. Okay, so how do you do this? So you need, you know, obviously when you go back to the picture of the memory, just like in the push and the pop, the processor might implicitly assign a certain register to handle these addresses, but the memory still needs a proper address. It needs a segment register and an offset address, which will together give it a proper a proper address to read and write from the memory, right? So what we are going to do is, we are going to say, let's assume that we are not going to assume, but the x86 typically allows you to use the source index register, okay, and it is pointing to some particular location. So you can choose and make this point to the blue data that you want, right? And let's say that the destination index DI is sitting here. Okay, so in this operation, what is going to happen is the source index will by default get associated with the data segment register. So when I say contents of SI, it means it is data segment colon SI, right? And how do you get the actual address? You do data segment into 0x10 and then add the source index, that's the offset address, and then you get the exact full address that you want. Okay, now therefore that's for the source index. Likewise, the destination index is going to be the extra segment colon DI. Okay, so what I can do now is to use the moves byte instruction to move 1 byte of instruction. That's why the B here, MOVSB, that B is actually going to talk about the byte, right? So you remember I said we use the word D word pointer or byte pointer earlier to refer that the address is now pointing to a byte of memory and not to a word or a D word, right? So that B is now implicitly suggesting that we are dealing with a byte of information and not a word or a D word, right? So therefore, you basically use this moves byte, okay, and implicitly this is going to do the following: move, okay, from source index to destination index. Okay, now this is a very interesting operation because it's a memory to memory operation that is happening directly here, right? So you're moving from source index. Now what is from source index? What is from destination index? It basically is this. This is what that contents of SI means, and this is what contents of DI actually means. So this is going to move data, but it not only does that, it also does something more. It basically auto increments or auto decrements after performing this operation, right? So let me take this off so that the DI will now become DI plus 1. Source index will become SI plus 1. Now, plus 1 or minus 1, it could actually, the processor can do plus 1 or minus 1, okay. Here, it could do plus or minus 1, and this depends on what is known as the direction flag in your flag register. So you remember the flag register the ALU operations would go and set some flags, the 0 flag, carry flag and all that. But there is also some bits that can be used by us and set or reset by the user through an instruction to specifically do certain operations. And one such operation is the direction of the source index, destination index, whether it's going to increment or decrement. So this one is, if the direction flag equal to 0, okay, it's in black. Maybe what I'll do is I'll put that in blue, right? This is when D equal to 0, or you could have the subtraction when direction flag equal to 1. Okay. So let us assume that we are executing this particular instruction. Okay, what is it? So we'll do the following first. We'll do CLD, okay, which is clear direction flag. Okay, this is the opcode or the mnemonic to clear the direction flag. So this is clear direction flag, right? So you can set it with an alternate instruction. I leave it to you to figure out what that mnemonic is. Please look up Google or ask ChatGPT, you will get the answer. Okay, so clear the direction flag. This implies auto increment. Auto increment. Okay, I'll just leave it at that. And then I say moves byte. Right? So what will happen here is, first the CLD clears the direction flag and it sets the direction of increment in the positive direction. So after the moves byte is executed, what will happen? Basically, you are pointing to some arbitrary location here, right? And you have this. Right. So what will happen now? When you execute the moves byte instruction here, the blue data from the source index will get copied here. Okay, and not only that, the source index will now increment and then point to the next memory location. So will the destination index. So after this moves byte is executed, automatically SI gets incremented by 1 points to the next address. Remember, the memory itself, this arrow here is increasing memory. So you start with 0x000 whatever all the way to 0xFFFF. Okay, that's how the logical memory is assigned, and you are going to go in that particular direction. So now you do moves byte, data has moved like this. Okay, now what you want to do, of course, if you were to just copy 1 byte of information, then no big deal in this, right? What is the great idea of providing a sophisticated instruction like this? So you need to be able to, the only additional thing that this does apart from moving data is to also auto increment the SI and DI, so that you are pointing to the next location ready for the next move instruction if you need. Okay, so now the idea is that we not only do this, but we also use another register. Okay, I'll tell you what that register is. We are going to use the CX register, which will store a count. Okay, ECX register. Okay, so this is going to implicitly store the count. of how many bits or how many bytes of information you want to move from this thing. So what you do now, if for example in this case I have 6 bytes of information that I want to move, so I will do move ECX comma 6 in decimal, right? I am just initializing the register to the value 6, right? And then I am doing clear direction flag so that I auto increment my this thing, and then of course I have to initialize my SI and DI, right, to these original addresses. So let us say this is offset source and this one is offset destination, right. So in that case what you do, you say move offset underscore source, move destination index offset underscore destination, okay, and of course now I have to do moves byte, but now I add a prefix to this instruction which is REPNZ. You repeat until non-zero. Until what is non-zero? Until ECX hits 0. Okay. So what will happen? This moves byte is only going to, let me copy this to the next page. Right. So what you are going to do is, you are going to do moves byte, and of course moves byte only increments SI and DI once to the next thing. But this REPNZ is basically it's a prefix to the instruction saying repeat until non-zero. So every time the moves byte, every time the instruction after REPNZ is, executed, ECX will be decremented by 1. Okay. So what will happen? You will start with this operation, at which point ECX will become 5. EDI will also be pointing here. Then you again do a moves byte. Okay. And yeah, then automatically my ESI will point here. Again you do, last one you do. Like this, you finish all operations. Then my data would have got copied exactly like this from the data segment to extra segment, and ECX will hit 0, and then you will stop sort of performing this operation. So this is the code that is needed to move 6 bytes of information from the data segment to the extra segment. Of course, the offset addresses are given by this OFF underscore SRC and OFF underscore DEST, right? Now, it's obvious that I might not want to only move bytes of information, I might want to move word of information, right? So therefore, there is also another thing which is called move, of course, so moves byte, right? It will move a byte, right? And then SI comma DI will auto increment, right? If direction flag is 0, moves word, it will move a word of information. SI comma DI will increment by 2 bytes now. Okay, this is only plus 1 or minus 1. This is plus or minus 2 depending on direction flag. Okay. Finally, moves D word. SIDI will increment or decrement by 4 depending on the direction flag. Of course, this is D equal to 0, 1, the direction flag, right? So, depending on that, you will do this. So, if you want to move like chunks of memory, right? So, for example, if I have the, this is again, I will draw the code segment and a stack segment in very small this thing. Let us say that this is my data segment, data and extra segment, right? And let us say that each of these rows now is a D word, is a 32-bit number, right? So, this one is some random data, okay? Then you basically have something in red like this and then in magenta, okay? This is my data that is sitting in memory, and my source index is going to be made to point to this guy, okay? And let us say I have done CLD, then I have moved SI comma SRC underscore offset. So, this one is SRC underscore offset, right? And then I have my destination index pointing somewhere here, okay? DI, which is destination underscore offset, okay? So, move DI, okay? So, if I now go ahead and do moves D word, okay, MOVSD, right? This is for D word because it is 4 bytes. Remember, each of this is now 4 bytes of information, right, or a D word, right? So, if I execute moves D, right, what will happen? My source index will increment by +4. Destination index, of course, first of all, the data from source index will get copied onto the destination index location like this, okay? And then my destination index register will also increment by +4. This is what happens after one moves D word instruction is executed, right? And just like we did in the earlier case, let's say I want to move 3 D words, then I would say move ECX comma 3. So, every time the moves D word is executed, it will increment SI and DI by 4, right? And therefore, but every time the copy also happens in chunks of 4 bytes, right? So, that is going to happen, and then I can put the same REP NE, right, or REP NZ. So, by the way, instead of REP NZ not 0, it is, you can also use REP NE not equal, right? So, you do moves D word. So, what will happen? First, it will increment by 4, the blue will be copied, then ECX is decremented to 2, then you do another copy where the red gets copied like this, the red gets copied like this, okay, and then ECX is decremented to 1, and then you further do another copy where the source index is now incremented by another 4, So is the destination index plus 4, and then you make a copy of the magenta, right, which basically is going to look like this, right, and finally ECX will decrement to 0, and then the loop will basically stop happening, right. So this REPNE is a suffix, right, which allows you to do a loop in hardware. Okay, remember this is not the equivalent of writing decrement ECX, jump on no 0 if it is not. I mean, as a pseudo code it may be okay to imagine it like that, right. However, all this is going to happen in hardware in one shot, and therefore remember this is what I would call a hardware loop. Okay, now it's needless for me to say that I can do exactly the same thing even if I wanted to copy word of information. What's a word? 16 bits or 2 bytes of information, where the SI and DI would auto increment by 2 instead of 4, and of course you have to appropriately load the count into ECX and do the same REPNE, right. So this is a very nice way of executing or moving data in a chunk from one location to another in just one shot. So if you look at the instruction that is actually implementing the copying operation, it is just this, the prefix REPNE and the MOVSD, right. So this is going to basically tie itself to the value of ECX, and then it will decrement ECX every time you do something. Likewise, this moves D is the operation that is moving the data from the source index to the destination index in every single operation.